These days, we are confronting a lot of energy problems concerning natural resources and power generation. When thinking about future energy, there will be wind power, water power, solar energy, nuclear energy, and so on. Today, we'd like to talk about nuclear fusion as a means of future power production which seems so unfamiliar to us despite its potential possibility. The idea of using human-initiated fusion reactions was first made practical for military purposes and nuclear weapons during World War II. Attempts at controlling fusion for power production had already started by this point. Registration of the first patent related to a fusion reactor was by the United Kingdom Atomic Energy Authority, and it dates back to 1946. This was the first detailed examination of the pinch concept. Since then, large efforts to experiment with the pinch concept also started at several sites in the US and in the USSR.
In the time since these early experiments, two new approaches developed that come to dominate fusion research. The first was Tokamak approach, which combined features of the stellarator and the pinch to produce a device that dramatically outperformed either. But in the late 1960s, the concept of mechanical fusion through the use of lasers was developed in the US, and Lawrence Livermore switched their attention from mirrors to lasers over time.
The magic of nuclear fusion is synthesis of usually two light atom nuclei and creation of one heavy. If synthesized nuclei are lighter than nuclei, reaction produces energy. On the contrary, synthesis of the two heavier nuclei absorbs energy. That is because we use fission to gain energy from heavier elements like uranium or platinum.
Deuterium with tritium, creating helium-4, freeing a neutron and releasing 17.59 MeV of energy as an appropriate amount of mass-changing forms to appear as the kinetic energy of the products, in agreement with special relativity. In the past, this process used for a hydrogen bomb, still which is used for the reaction of fusion reactors, most likely achieved, seeing 17.59 MeV of energy as an appropriate amount of mass-changing forms to appear as the kinetic energy of the products, in agreement with special relativity. In the past, this process used for a hydrogen bomb, still which is used for the reaction of fusion reactors, most likely achieved.
Experiment facilities are under construction in various places over the world. ITER is in Cadarache, France. IFMIF is in Rokkasho, Japan. NIF is in Livermore, the US. In these areas, the projects provoke strong protests from residents.
Fusion power has great potential as a new energy. Fusion power uses deuterium contained in seawater as fuel. It means that we have an almost infinite supply of fuel. In theory, fusion power can produce 100 trillion joules from 1 kilogram fuel. That is 10 million times the energy with the modern rocket engines. It is expected to be available for new propulsion systems for interstellar navigation.
However, the new technology and the risk always go together. It also has some demerits. First, in order to realize the ideal condition, gigantic facilities and immense budget are necessary. Nuclear fusion process can occur only in extreme heat and extreme pressure. Second, the risk of radioactivation still exists. Neutrons made by fusion processes are possible to turn the wall of reactor radioactivate.
A paper published in January 2009 and part of the IAEA Fusion Conference proceedings at Geneva in October 2011 claims that small 15 MW tokamak-style reactors are feasible. However, there are still significant barriers standing between current scientific understanding and the partial realization of fusion as an energy source.
The energy which is takeable from nuclear fusion is not so high compared with the energy which is given to keep plasma's high-pressured condition. The ratio of the takeable energy to the given energy is now 5:4. So now, many researchers are trying to get the ratio higher and higher.